And we're live. Hi. Hi,
Hi.
Deirdre. How
Hey,
are you?
Kristen. I'm doing well. How are you?
I'm doing so well. I'm Kristen with MAA Communications, and I'm here tonight with Deirdre Smeltzer, who is our Senior Director of Programs and Competitions. And we're
Yes.
excited.
Yes, we are very excited. I am so happy to welcome everybody to our very first virtual distinguished lecture. And so if you're here and listening, we'll start the program in just a minute, but feel free to drop where you're tuning in from into the chat. We'd love to know where everybody's watching from. That's one of the big advantages of going with the virtual format as opposed to the previous in-person lectures that we had at the MAA Carriage House. People can tune in from anywhere. So we're really thrilled to be making this move to a virtual format for the Distinguished Lecture Series.
Absolutely. Well, tell me a little bit about what it was like for you to reimagine this lecture series in obviously the environment we're in now and doing this virtually. And tell me a little bit about who you've chosen for this first season of it.
Yeah. Well, so as with everything in 2020 and 2021, we realized we could do a lot of things virtually that we previously did in face-to-face format. And so in early 2021, the MAA started a virtual programming series, which I also encourage people to check out. And as part of that conversation, as we were sort of seeing how that unfolded, we realized that just as the virtual programming, which is a variety of types of events, allowed us to reach more people, going virtual with the Distinguished Lecture Series would allow us to, as I said, make this accessible, this really great kind of long-standing series of mathematical talks available to a much broader audience. And so, yeah, we really just, we want to think about how to make this engaging and interesting to a really broad audience. So we are looking for mathematicians from many different fields to talk about their expertise and do so in a way that is interesting and accessible for a broad mathematical audience. So we are really thrilled that Dr. Pamela Harris is our very first speaker.
Absolutely. Well, thank you for that introduction to the relaunch series. And I am going to hop off and let you get started. And I'm going to bring on our executive director, Michael Pearson, who is going to introduce Pamela for us. So,
okay, thank you so much, Kristen.
Michael.
Yeah. Okay. Well, let me just welcome everybody again. We are ready to start the program itself. And I want to thank everybody for joining us for this very first virtual MAA Distinguished Lecture. This is our first one. We will have 2 more this spring season. But I now invite our executive director, Michael Pearson, to introduce tonight's speaker.
Well, thank you very much, Deirdre. I'm glad to be here. As you and Kristen were talking, I was watching the scroll of comments and seeing we've got people from all over the U.S. as well as Australia and Canada. So it's great to have all of you with us in this virtual setting. Hello.
Hello.
And it is really a pleasure for me personally to be able to introduce tonight's speaker, Dr. Pamela Harris. Dr. Harris serves as Associate Professor in the Department of Mathematics and Statistics and Faculty Fellow of the Davis Center and the Office of Institutional Diversity, Equity, and Inclusion at Williams College. Dr. Harris co-hosts the podcast Mathematically Uncensored and serves as president of LATHISM's, Latinxes and Hispanics in the Mathematical Sciences. Dr. Harris's research interests are in algebra and combinatorics, particularly as these subjects relate to the representation theory of Lie algebra. Dr. Harris has some 36 papers either submitted or already published and a bunch of other papers on pedagogy and issues around the mathematical sciences community. And it's been great pleasure to get to know Dr. Harris over the last few years. One publication I will mention in particular, Dr. Harris was co-editor of Testimonios, Stories of Latinx and Hispanic Mathematicians, which I just want to point out, if you're an MAA member, you can download that publication at no charge from the MAA member library. So please, if you're not a member, it's a good reason to join, so you can download that book. Pamela, I understand that for fun, you like to deadlift heavy things.
I
Now,
do.
what in the world are you deadlifting?
Just weights. You know, you got to stay
Okay.
strong.
All right, then. Well, that is, that I'm sure it's good for you, but it doesn't sound pleasant to me right now.
Oh, no, it's amazing. Get out all that aggression, you know?
Oh, okay. Well, that's
People
good.
go for runs. Some of us just lift really heavy things, put them down and lift them again.
Okay, then. A rather Sisyphean task, I think.
It is.
Well, anyway, it's great to have you with us tonight, and we really appreciate you accepting the invitation, and I'm looking so forward to the talk. So with no further ado, let me turn it over to you.
Awesome. Thank you so much for the introduction. That was just so lovely. And yeah, I also see friends in the chat. So thank you everyone from all over the country for tuning in and checking out a little bit of what I want to share with you tonight. So let me go ahead and pull up the slides. Excellent. Okay, so you're here because I tried to entice you with what is this connection between some objects called multiplex juggling sequences and then this other thing called Kostant's partition function. So I expect that you haven't seen any of these things. And so I'm going to just start from basics. I'm going to introduce what is mathematical juggling, but also introduce what are vector partition functions. And really the whole pinnacle of this talk is to tell you how these two things are, in fact, the same thing. That's really, really the big idea in this entire talk, that these two very different looking objects are, in fact, combinatorially equivalent. So that's the show for tonight. All right, so let's get started. Now, with juggling comes a long history. And so I wanted to highlight some key aspects of it. So you can see in this depiction, and I apologize already because we were hoping that I would have a laser pointer, but it didn't work out. But I hope that you can see that there are some figures here depicted, which are tossing some objects up in the air. And so this is coming from a painting in the wall of Tomb 15 at Beni Hassan. And so 4,000 years ago, we have these images of people juggling. Now, you don't have to travel very far. You can go to ancient China and also see that happening. So in the middle panel towards the left-hand side, you can see a juggler in this market. And so this is from a mural section of the Dahuting tomb of the late Eastern Han Dynasty. And so in China, also, we see depictions of juggling. We can also go to ancient Greece. And so in this piece, in this figure, you see that there is a person sitting and they have these kind of little two objects that they're tossing in their hand. And so we see juggling or acrobats and other kinds of skill games that appear frequently in either the tomb reliefs, sometimes in coins, and even in a vase like the one presented here. Now, you might think, okay, great. So juggling has a very long history. Where do we see the intersection between juggling and mathematics? Well, one of the earliest juggling mathematicians that we actually have some history on is Abu Sa'al al-Kuhi. He lived around the 10th century. And before he became a very famous mathematician, he actually spent his time juggling glass bottles in the marketplace of Baghdad. And so part of his contributions to mathematics is that he created this perfect compass, that's what's illustrated in this slide, to draw conic sections. So that's part of his mathematics. What about other cultures? Well, you can go to 1528, and the Emperor Babur of Hindustan described in his memoir a group of jugglers who would simultaneously spin rings on their forehead, thighs, fingers, and toes. Now, if you grew up in the US, it was often commonplace that when you're, in middle school or even elementary school, you get to play with, like hula hoops. And so I don't know if you ever did this, but sometimes you would stick hula hoops in your hands and then you would swing your arms and then you would have all these rings kind of spinning. So now imagine having those on your forehead and on your thigh, on your fingers and your toes. And so people had quite a strategy for these kinds of juggling games. And then often you can toss them, of course, and catch them. If you were, I was never very good at it, but I remember my friends would toss them and then like do some flips or something and then catch them behind their back. Quite entertaining. What about, again, other cultures? Well, you can also see in this depiction, so this is a painting by Christopher Whiteitz, around 1528 is when the Aztec Antipodis jugglers were taken to Europe by Hernán Cortés. So the history isn't so nice, but the point here is that we would juggle with our feet. So Aztecs were known to juggle these objects, but with their feet. So make it a little bit harder. Why don't you? There's also some depictions of juggling among the Naskapi, the Eskimo, the Achomawi, the Bannock, the Shoshone, the Ute, and the Sunni tribes of North America. And so this is well documented in the work of Stuart Cullen in his book titled Games of the North American Indians. So more close to home, we also were juggling for a long time. And then I really like this quote. So Maximilian said the following. So women are expert in playing with a large leather ball, which they let fall alternately on their foot and knee, again throwing it up and catching it, and thus keeping it in motion for a length of time without letting it fall to the ground. Prizes are given, and they often play high. The ball is often very neat and curiously covered with dyed porcupine quills. So I imagine that might be a little painful, but what I really wanted to highlight about this is that very seldomly do we get something written that says that women are experts. And so I wanted to highlight that in this talk. Now, what about juggling now? What's happening with juggling? Well, I wanted to share this story because I find it inspiring, because there's some history that says that at the International Juggler Association, this became a thing when a group of jugglers attended a 1947 International Brotherhood of Mathematicians convention. So they had attended, imagine like attending, let's say, the joint math meetings or MAA Math Fest. And you hang out with your friends at this, let's say, magic convention. And you're sitting around and you're like, listen, juggling is substantially different than hiding a bunny and pulling it out of a hat. So shouldn't we have our own organization? And so I imagine that they might have gone to like a conference dinner, very much in the same spirit of what we do as mathematicians. When we go to a big national conference, we get together with our math friends and talk about the kind of math that we like. So you might imagine that you have a branch off where you have sessions only maybe in analysis or only in combinatorics. And so you start having these special topics conferences in mathematics. Well, very much that is what happened with the jugglers. And so that's how they started their own association for juggling. Now, great. So they have their own association for juggling. And what is the connection between juggling and mathematics? Well, the main thing is that people want to be able to talk to each other. When you're a juggler and you have juggler friends, you want to be able to tell them about your new tricks. And you want to be able to compare, is my trick different than your trick? And if so, how are we going to communicate that? And so they developed this notation, which is often called site swap. And it's used to really just describe the way in which the objects are being thrown. And so it turns out, this is the beautiful part and why I love math, is that you can use mathematics to make this very precise and to condense a lot of information into sequences of numbers. So that's the plan for now, to now think about how we're going to mathematize juggling. All right, well, like any good mathematics, you need some initial assumptions to make this as straightforward as possible. So the first thing we're going to do to describe some sort of juggling pattern is the following. We're going to begin very simply by assuming that a person can only juggle with a single hand and that they can only hold a single object at a time. Now, later in the talk, we'll extend this a little bit further, but for now, this is going to be our initial assumption. So again, you juggle with one hand, and you can only catch a single object at any given time during the juggling. The other thing is, because we're going to assume that this juggling goes on forever, so this person is just going to juggle for eternity and has been juggling since eternity. Now, the other thing to keep track is the heights of the objects. So when I throw, I'm going to imagine that I throw it to some positive integer height. Okay. And then every unit in time that passes, I'm going to imagine that the ball lowers by a single unit in height. So that's our key here. So every unit in time that transpires, the ball drops by a single unit in height. And of course, you know, once it gets to 0, you have to catch it, and then you can throw it back if you want to. Okay, so those are our assumptions. And I also am happy to see that there's some conversations in the chat, so please keep those going. All right, this is by far the only thing I can juggle. Okay, so here's a little object, and help me, Lord. Here we go, being recorded. Okay, 1, 1, 1. Okay, that's my juggling. That's as good as that's going to get, friends. So if you were going to clap, that is the minute to clap. All right, so the juggling pattern 1, 1, 1 forever just means that you start with an object at hand. So these little circles, I imagine, are your hand. And then you toss the blue object. So that's the blue arc. You toss it to height 1, which means that 1 second later, you get to catch the object again. You toss to height 1, catch, toss to height 1, catch. Continue that indefinitely. Wash hands, somebody did say. Yes, I guess, you know, we are being safe. So if you're juggling objects, make sure you wash your hands before handing your juggling objects to your friends. Here's a little bit more interesting of a juggling diagram. So in this case, we're keeping track of the heights again. So those are the numbers underneath. And in this case, I'm going to juggle the pattern 3, 3, 3 indefinitely. Notice that the arcs are colored in 3 colors because it turns out that there are actually 3 objects being juggled. So I colored them green, red, and blue just to make them a little bit easier to see. But the key here is, suppose that you start with a blue object, it's at hand, you toss it to height 3. So you know that 3 time steps later, you catch the blue at hand again. But in the interim, after tossing the green to height 3, you catch the green. And then immediately toss it to height 3. 1 time step later, you catch the red, you toss the red to height 3. And then the next time step is when the blue object comes back to hand. So that was already 3 time steps later. Okay, great. So that is the 3, 3, 3 forever juggling pattern. Now, here's a more interesting one. And again, I'm color coding the arcs so that you can keep track of which object it is that is being juggled. So this pattern is, you can read it at any point as long as you repeat the length of the sequence. So this is either the 015 or the 501 or the 150 pattern. Okay, so you pick wherever you start. So maybe we'll start right on the left-hand side. So at that time step, I have a 5 underneath me. So I have just caught the blue object. I'm going to toss high to height 5. So if you count 5 hand steps after that, or time steps after that, I see the blue return to my hand, at which point I would toss it short. So a height 1, catch again, toss to height 5. Now in the interim, when I had thrown ball, the blue, 5 units, notice that there's a 0 after the 5, which means I never tossed that object. There was no catch, there was no toss. I kind of just stood there and watched the objects kind of flying above me. But 1 time step later, underneath the object with a 1, I caught the red. So I had thrown at some previous point the red, I catch the red, I toss short, then toss high to height 5. And so you can iterate this process and you see that this forms, again, a juggling diagram. Okay, great. So at this point, I've shown you 3 different ones. And one thing that people might start thinking about is like, maybe every sequence of numbers results in a juggling pattern. And the answer is actually no. And so very quickly, we see that this example does not work. Why? Remember, one of our assumptions is that we can only catch a single object at hand at any one time. So if we start suppose that you start at the number 1. Okay, at that point, somehow you caught this, black object, you toss it to height 1. Okay, now it lands on the 2, but somehow you had tossed this purple object at a height 2 previously. And so you get at that one-time step, both the black and the purple in hand, which is not allowed. Of course, again, we can extend the definition, and then in which case maybe this is a juggling sequence, but at the given time that we have our assumptions, this one is not. Okay, great. So the question is, what if I just give you some sequence? So suppose this 4, 4, 1, 3, and we want to determine whether this thing is a juggling sequence. Now, I've given you these diagrams. So what you could do is literally grab some paper and a pen and actually start drawing out this pattern. And then seeing if you ever run into the problem like we saw here, where you catch maybe 2 or more than 1 object at hand, and then you could decide, okay, this is not a juggling sequence. So you might do that in your spare time. And if you're following maybe the recording, not the live version, you can pause here and actually try that on your own. Okay, I counted, pretending somebody eventually in life is going to pause the video there. But now let me just show you the picture. So here's the picture that I created using that pattern. So 4, 4, 1, 3. And I can't tell because I didn't color coded how many objects there are. It looks maybe 3. Do I see some agreement maybe in the chat? I think I see 3 objects being juggled. So the one that goes, if we start on the left-hand side, you have a 1. Then it goes 1, 3, and then 1, 3, 1, 3, 1, 3. So that object is part of the juggling sequence. And then there's the one that hits one of the 4s. And then there's another object that hits the second 4. Okay, now imagine if I gave you a sequence that had way many more numbers in it. Making these pictures might actually not be the best option. So we want to come up with a mathematical way in which we can test whether some sequence is actually juggable, meaning can we actually juggle? All right, so here's where algebra comes to the rescue. So we already know that this 4, 4, 1, 3 is juggable. We just saw the picture of it, and we didn't run into any problem where we caught 2 objects or more than 1 object at a hand. So we know we can do it. But here's how we're going to test any sequence that's given to you. So here's what we're going to do. First thing, we need to define the period, and that's just the number of numbers in the sequence. So in this case, we have 4, 4, 1, 3, so 4 numbers. So this sequence has length 4. We call that the period. Now, what I'm going to do to those numbers is I'm going to add 0, 1, 2, and 3 to that sequence that we're trying to test, okay? And because, algebra and arithmetic sometimes gives me trouble, even with a PhD in math, I did this ahead of time. So we're going to take the 4, which is the first number in our sequence. We add 0 to it. That gives me 4. And then 4 plus 1 gives me 5. And then 1 plus 2 gives me 3. And then 3 plus 3 gives me 6. So that's our new sequence. Here's what we're going to do with it. I'm going to take 4, 5, 3, and 6. And what I'm going to do is basically reduce them modulo the period, meaning you divide by 4 and then just keep track of the remainder. So I take 4, divide by 4. Okay, great, no remainder. I take 5, divide by 4, remainder 1. 3 divide by 4, remainder 3. 6 divide by 4 has remainder 2. So after I do this process of adding 0, 1, 2, 3 to the elements of my sequence and reducing modulo the length of the sequence, I get this new thing. This new thing is called a test sequence. And the big theorem says the following. If the test sequence you construct from your original sequence consists of all distinct numbers, so notice what did we have? 0, 1, 3, 2. They're all distinct, none repeated. Then in fact, the original thing you started is juggable. And then the converse also holds. If they're not different, then you can't juggle, right? Okay, so algebra to the rescue, right? Here's mathematics. So now if somebody gives you a juggling sequence, you can test it much quicker than having to draw these periods where you're trying to draw the arcs between them. Okay, so now we want to generalize. what happens in the case where we can actually hold more than a single object at a time in any one hand? Okay, so this is then, oh yes, I love the word juggable. I see in the chat somebody says it's my new favorite word. It's been mine as well. All right, so here's what we're going to do. We need some new definition if we're going to now allow to hold multiple objects at a hand. So we're going to define a multiplex juggling state. So that's our first thing. And then eventually I'm going to add the word juggling and get rid of the state. So all this is telling me the way in which the objects are at some time step. So the configuration of objects in the air. Now, the way I'm going to do that is with a vector, because a vector allows me to think about position and then also a number at that position. So if you look at the example in the bottom here, I have a vector listed as 2, 1, 1. Now, I try to think of, because I need to describe height, I think of this as a conveyor belt with buckets at different integer heights. So the bottom bucket of this conveyor belt is holding 2 objects. That's depicted in the vector as the first entry being a number 2. Then I look 1 bucket up. So that's the bucket at height 2. There's only 1 object in that bucket. That's depicted then by the second entry in the vector, which is a 1. And then I look 1 bucket higher. That's at bucket number 3. There's 1 object there, and that's depicted in the vector with the 1 at the end. How are we doing? So again, the ith entry of the vector tells me how many objects I have at height I. That's really the main key here. So this is just a single time step. Now what we want to do is we want to put those together. Okay, so let me give you this example. So again, how are we going to do this? To define this juggling sequence, it just needs to make sense that we can go from a particular configuration of objects in a single time, and that one time step later, the next distribution of objects in the air makes sense, okay? With the idea that every time step that you go, the objects lower by a single unit in height. Okay, so let's suppose that we play here with this initial state, which has 1 object at height 1, 1 object at height 2. Okay, so what's going to happen one time step later? The bottom bucket is going to give out, and all the other ones lower by 1. So if there is an object in the bottom bucket, you get to immediately redistribute it in some of the buckets above. So in this case, I'm going to move from this juggling state to this particular juggling state. So let's think about what happened. In the first picture, I had 1 object in each of the buckets. The bottom bucket fell out. So I'm holding an object and I need to redistribute it. Okay, so keep that in mind. But notice that in that same first picture, there was an object at height 2. In the next picture, it lowered into bucket 1. Again, because all the buckets in the conveyor lower by 1 every time step. And then what I chose to do with the object that had fallen is I just stuck it in the first bucket. Okay, so we move from the state 1, 1 to the state 2. Now, in the next time step, both objects fall to my hand and I must redistribute them. I'm going to redistribute them in this way. So I get 2 new objects and I put 1 at height 3 and 1 at height 2. And so now the state is illustrated by 0 objects at height 1, 1 object at height 2, and 1 object at height 3. And now notice that in the next time step, I actually can't do anything. It's completely predetermined. The objects are just simply going to lower 1 unit each. And so we go from the vector 0, 1, 1 to the vector 1, 1. Okay, so now here's the question that we have. This picture is what we call a juggling sequence. The beginning image is what we call the start state. So this is how we started. That's the initial distribution of the objects. The final one, it doesn't always have to be equal to the first. My picture just does. But the final picture is what we call the end state of the juggling sequence. The length is how many time steps transpired to get us from the start state to the end state. Well, in this case, I just count the arrows. So there's 3 arrows, so we had 3 time steps. And then I can introduce what we call the hand capacity, just meaning how many objects can the buckets hold maximally. All right, so you can decide maybe it's 1, and then we're back to the standard juggling that we saw previously, or you can make that higher, and then now you're really truly a multiplex juggling sequence. And so our goal is to figure out a way to count these sequences. So how can we count them? And then just to simplify notation, I'm going to use the MJS, so for multiplex juggling sequences, parentheses SEMN to denote that count. So that's my notation for a number, meaning the number of juggling sequences that start in S, end in E, have a capacity of M per bucket, and do so in time step N. All right, so let's look at an example. So this one starts with the 1, 1. It's going to end with both objects in the bottom bucket. So that's the vector 2. We're going to do that in 3 time steps. And I'm just going to force that the hand capacity is as big as it can be, which is, well, 2, because there's only 2 objects. And now our goal is to try to calculate how many multiplex juggling sequences there are. So let me start with this one. So notice 3 arrows. So we know that we did 3 time steps. And I already know what the first picture should be and what the final picture should be. Regardless of what happens in the middle 2 distributions of objects, the final and the start are fixed. And now I just need to figure out what's going to happen. What are the objects that I can actually move? If you notice from the first time step, 1, 1, to the next, the object at I can do this. The object at bucket 2, so at height 2, simply lowers by 1. So I don't get to throw that object. That one just is always going to be predetermined. Now, the bottom object I get to throw. And so in this particular example, I threw it to height 3. And then what happens? At the next time step, the one that I had just thrown to height 3 will lower. The object that was now at height 1 falls to my hand, and I happen to just redistribute it into the same bucket that I had an object at. And then at the last time step, they just lower, and they land where I needed them to land. They needed to land at the bottom bucket. Okay, so you can convince yourself that you can do this very meticulously by figuring out how high you can throw the objects and then diminish the height as you need to. So this is one juggling sequence. Here's another. Notice that I just didn't throw so high at the second time step. And then here's another. Here's another. Here's another. Here's another. Notice that one's kind of interesting because in the first time step, one of the objects always lowers, right? I don't do anything. And then I just put the ball that fell, I put it into the bottom bucket. They both fell, put them into the bottom bucket. They both fell, put them into the bottom bucket. Okay? And then finally this one. And so it's not super easy to just look at this and say, oh yes, of course, the answer is going to be 7. And the problem always in combinatorics is if you're trying to count, you want to make sure you count everything and then also that you didn't double count anything. And so it can be quite tricky to decide how you're going to be meticulous about this organization of these patterns to ensure that you get them all and that, you don't miss any and that you don't double count any. So anyways, I say all of that to say this is a fun game, but it requires some caution. Okay. Now I'm going to just do an about face. And I want to introduce a new set of characters. Okay, they're called vector partition functions. So here's the technical slide. So it says the following. We're going to start with a matrix. It's going to have integers in it. It has m rows, d columns. And the goal of a vector partition function game is you give me this matrix, and I want to find the solutions ax equal to b. So someone comes in, I see Daniel is watching. So Daniel has a favorite vector. His vector is B. My entire goal is I have matrix A, and I want to figure out in how many ways could I write Daniel's favorite vector B as a non-negative integer linear combination of the columns of my matrix. That's the game. So somebody comes in, favorite vector, And my goal is to say, I can write your vector as a sum of my columns of my matrix A in this number of ways. Now, somebody might think, well, where does this show up? Why do we do this? And in fact, there's so many applications. So you can start in number theory, studying partitions. You can also, and this is the way that I came to work on vector partition functions, come from representation theory, maybe via weight multiplicities. You also might study Hilbert series because you're a commutative algebraist, or maybe you're an algebraic geometer who likes to study toric varieties. So these kinds of computations show up there. Or you love discrete geometry. Maybe you like counting integer lattice points inside of some polytope. This also shows up there. Or maybe you love applications and you want to do some integer programming to optimize a solution to something. And so this also shows up there. So lots and lots of places where vector partition functions show up. All right, we're going to focus on a particular family of vector partition functions. Now, a vector partition function comes with a matrix. And so as long as you tell me what the columns of that matrix are, then I have a complete partition function problem at hand. So the partition function we care about is named after Bertrand Kostant, who recently passed away. And a little tidbit of a story: when I was a PhD student and I published my first paper, afterwards, he sent me an email. And I treasure that email because he said something to the effect of, "Great work. I saw your paper. I really liked it." And then I was like, "Oh, Kostant read my paper." And so if you're in the audience and you're someone, who gets things named after you, and there's a young mathematician who is blossoming and you see a result that you like, make sure you email them. It really does change the way you feel about your mathematics when, a famous MIT professor emails, a young mathematician. It's quite memorable of an experience to have gotten that. But so here's the vector partition that he defined, or that's named after him. The columns of the matrix are what are known as the positive roots of a Lie algebra. Now, I could give you a whole talk about what Lie algebras are and why people care, but really, for our purposes today, all I need is to explain to you what those columns are so we can eventually get back to juggling. So here's what the positive roots are for the Lie algebra of type A sub R. So I start with the standard basis vectors of r to the r plus 1. So again, EI, that's just a column vector with zeros and ones, all zeros except a 1 at the ith position. And then what I'm going to do is I'm going to create these little alpha i's, which is just a consecutive difference of those standard basis elements. So EI minus EI plus 1. And then I'm going to start adding those together. So I'm going to throw in all of the what we call simple roots. So the alpha 1, alpha 2, all the way to alpha r. And then I'm going to start adding. I'm going to take some alpha I plus alpha I plus 1 plus alpha I plus 2 all the way to wherever I want to end, alpha sub j. They just have to be consecutive. So if you start with alpha 1 and you start adding to alpha 5, you have all the ones in between. Okay, so consecutive sums. And that is the set of positive roots of type A. Those are the columns of the matrix that we're going to use to define the vector partition function. So let's go very precise. Let's look at A2. So in this case, we have an alpha 1, an alpha 2, and again, consecutive sums. Well, there's only one, alpha 1 plus alpha 2. And then I depict them there for you in vector notation. So notice alpha 1 is E1 minus E2. So that has a 1 in the top position, a minus 1 in the middle, and 0 in the third. And likewise for the other two. You just add the EIs that are appropriately based on its definition. So the matrix that we create are coming directly from those vectors. So that's the matrix A. And then I play the game again. So somebody comes in, I see Professor Steve Butler on the call. So he comes by and he says, I have vector B. It is my favorite vector in the column space of your matrix. So then I show up and I'm like, I want to count in how many ways I can write Professor Steve Butler's vector B as a linear combination of the columns of my matrix A. But notice I'm only allowed to use the columns a non-negative multiple of them. Okay, so I don't get to use like half of column A and half of column B. Okay, I don't get to do that. They're either 0 times or 1 or 2 or 3 and so on. Alrighty, so that is the game. Now, the first question what might say is, well, what if you give me this vector B that happens to be n1 multiple alpha 1 plus n2 alpha 2? So for some natural numbers, n1 and n2. And I hope nobody gets upset, but 0 is in my natural numbers. It happens that you can then, based on the matrix A I just showed you, the number of ways I could write that vector B is, well, the minimum of the two coefficients that define B plus 1. So why? Well, it just requires that you keep track how many times you're using the positive root that is the sum. So alpha 1 plus alpha 2. So maybe you don't use them at all. And then you use n1 alpha 1s and n2 alpha 2s. So not using that root is 0, right? That alpha 1 plus alpha 2, you use it 0 times. Or you can use it 1 time or 2 times or 3 times. But the most you could use it, so to ensure that the coefficients of the remaining columns are non-negative, is the minimum of those coefficients that define B. And so how many? Well, 0 all the way to the minimum. That means that there's the minimum plus 1 many ways that you can do it. So that's usually the initial proof that you see as you're working on Kostant's partition function. It's like your first exercise that you get to work on. And then you think, well, gee, this is a whole family of partition functions, right? You change the subscript and the type. So instead of A2, maybe you look at A3. What happens in that case? Okay, we try to play the game. So I just went through and I put in all the vectors. Notice I have the simples. So alpha 1, alpha 2, alpha 3. And then I start taking the consecutive sums of them. Here's the matrix. So I gave this very same problem to a set of students at Williams a few years ago. And I said, think about it. Tell me what you find. And then they came back, a few weeks later after we, went through all the details. And they said, here you go, Professor Harris. And then I was like, oh, no. Oh, yikes. I did not foresee that getting so bad. And then I thought, okay, this requires me to do a lot of computation. Can you make some restrictions, make some choices about the relative size of the coefficients n1, n2, and n3, and maybe close the formula so I don't actually have to compute so many of these minimums and the sums and all of this? And they said, yeah, we can do it. Super eager. They went away for a little while. We worked some more. And then they came back and they said, ta-da! And then I was like, oh, no, that's still really hard. And I was like, okay, but it works. So if you notice in this initial result, this theorem, they make some decisions as to the relative size of the coefficient. So for the first one, they say n1 and n3, let's just suppose that's bigger than n sub 2. And then they can give you a formula. And in fact, it's a beautiful formula. It's this corollary, which I just highlight. So it's that part of the theorem, the first part. It gives you tetrahedral numbers. So all of a sudden, the number of ways to write a vector with this inequality condition on its coefficients is given by the tetrahedral numbers. And so there's some nice enumerative results that show up. Now, I got to admit to you, going to A4, A5, A6, it's just not tractable. Unfortunately, there are no known closed formulas for Kostant's partition function. So these problems are really difficult. In fact, what you saw them do by making those assumptions about the coefficients is they were decomposing the space and trying to find a polynomial that satisfied that system of equations. And in fact, Blakely showed that, yes, you can decompose the space n to the d so that the partition function on each of those pieces is in fact a polynomial of degree n minus d. But figuring out how to do that, how to make those choices of how to decompose the space is actually very difficult. And people spend a lot of time just trying to figure out what those choices ought to be so that then you can get this polynomial that you're looking for. So lots and lots of things remain to be done. But now I want us to connect these two ideas. So here are 3 vector partitions of the vector twice alpha 1 plus twice alpha 2. So again, I can just use the simples. So here, notice that these are multi-sets. So I'm using alpha 1 twice, alpha 2 twice, or I can use alpha 1 and alpha 2 a single time each, plus alpha 1 plus alpha 2. And then the last one is I use 2 copies of the positive root alpha 1 plus alpha 2. All right, so 3 vector partitions. There are 3 juggling sequences that start and end with state 2, have hand capacity 2, and length 2. And of course, if I give you 3 apples and 3 oranges, like, yeah, sure, they're in bijection, but that's probably just a coincidence. Or is it? So what you should do then is go into the online encyclopedia of integer sequences. And we saw that it wasn't a coincidence because we said, well, what if we just bump up the 2 in the juggling sequence up to a 3? Start with state 3, so the 3 objects at the bottom, end with the 3 objects at the bottom, and have hand capacity 3. And so we saw these numbers. And then we put them into our program that counts the solutions to the Kostant partition function, and they were the exact same numbers. And so now there's something interesting happening. And this is where we talk about a bijection. So here's my math friends. So Carolina Benedetti, Christopher Canusa, Alejandro Morales, and Anthony Simpson and I worked on this problem where we actually establish that these 2 things are exactly in bijection. So the number of things, the number of solutions to the partition function problem for this vector, so n times the sum of all of the simple roots, which is actually called the highest root, is the same number as the multiplex juggling sequences that have the same start and end state with the n objects at the bottom. Hand capacity is not playing a role. And notice that the time r is exactly the r that's indexing the positive roots of the Lie algebra. So we got this result. And I want to show you the most beautiful key insight that was needed to do this. So what we do is you just have to keep track of when you're throwing an object and to what height. So every throw at time I to height j is encoding a vector, ei minus ei plus j, which is actually just the consecutive sum from alpha sub I to alpha sub I plus j minus 1. So there's a little minus 1 at the end. So let's look at this application of that key insight. So again, I showed you the pictures. There's 3 juggling sequences with those parameters. There's 3 partitions of that vector. And now let's just go very carefully and figure out the throws. So let's start with the first juggling sequence. So it's this one. So what happens? Well, notice that at the initial time step, at time 1, I'm throwing 2 objects to height 1. Well, that's giving me 2 vectors, 1 for each of the throws, of the kind ei minus e2, which is just alpha 1. Let's see what happens at time step 2. So at time 2, I'm throwing 2 objects to height 1 again. Okay, so that means that I now have 2 vectors of the kind e sub I, in this case e2. Oh, that should be a minus. I apologize. That should say e2 minus e3. Every good talk has typos. That's one of them. So that's alpha 2. Well, that means that if I put those together, that corresponds to the vector partition alpha 1, alpha 1, alpha 2, alpha 2. So if I sum them up, I do get the vector I was looking for. 2 alpha 1 plus 2 alpha 2. All right, let's look at the next one. So in this case, what happens? I throw at time 1, one of the objects to height 1. So that's the one that goes in the bottom bucket in the middle picture. That gives me the vector e1 minus e2, which is alpha 1. Then I throw, again at height 1, another object, but I throw it to height 2. So that becomes an e1 minus e3, which is alpha 1 plus alpha 2. And now look at what happens in that last time step. Only one object is actually thrown. I throw an object at time 2 to height 1. That gives me the vector, and there's a typo there again. So that's e2 minus e3, which is alpha 2. Copy paste error. So I get then the vectors on the right-hand side summing up exactly to alpha 2, sorry, 2 alpha 1 plus 2 alpha 2, which is the vector we were looking for. Now let's look at the very last one. In this case, I throw 2 objects at height 1, at time 1, to height 2. So I toss them to the second bucket in the middle picture, which corresponds then to the vector E1 minus E3, which is alpha 1 plus alpha 2, 2 times, because I threw 2 objects in that way. And so that's that final partition that I was looking for. And so in fact, that application of that key insight that the throws at a given time to a certain height encode a vector allows you to then create this bijection between these sets of objects. And so the beautiful thing is that we were able to extend this result to consider other Lie types. It did require us to think about something which we call magic multiplex juggling sequences. But, my time is up. And so what I'll do is I will just point you to the technical reference where we do that. So this was published in the Annals of Combinatorics in 2020. And so it's given, the article is named after the same talk title for today. But I also wanted to point out for the interested reader who just wants to see this talk, but maybe in print, you can check out 2 expository references that were published in the Girls Engle Bulletin. And if you're so kind, you should support them. They have a ton of phenomenal content, and you should consider submitting your expository articles. My idea is always, if you have a technical piece of paper, that you've written and you're very proud of, we should always work to make it so that other people who don't have maybe all the Lie algebra background, which you notice was not necessary, let's give everybody some new mathematics to learn. So let's make it as accessible as possible. I think we can always do it. So with that, it's been such a fantastic honor to have the opportunity to speak to you tonight. Thank you so much, MAA, for starting this program or restarting this program in this new format. It is always a pleasure to work with the Mathematical Association of America. You make this mathematician proud. Thank you so much for the community you build. Thanks, everyone. Happy to answer questions. Oh, Deidre, you're muted.
Right. Sorry, just realized that. Thank you so much, Dr. Harris, for a wonderful talk. That was really fascinating and just really extremely well presented. I hope you can see all the affirmation coming up in the chat. For those who are in the audience, we're going to have a few minutes for Q&A. So be thinking about what comments or questions you would like to ask Dr. Harris. I want to also just mention 2 quick things. One is, as Pamela mentioned, this will be viewable in the future. So if you want to go back and rewatch and follow along, fill in details, you can do so. You can also share it with others who aren't here but would be interested in the talk. And one other comment, we will be putting in the chat a link to a short post-event survey, which we would love for you to take, so you can give us some feedback. But in the meantime, if we have a few minutes, if people would like to ask questions about any part of the talk or related topics, please feel free to put those in the chat, and we will highlight them for the audiences in both platforms, Facebook and YouTube. So, Pamela, I'll just ask. I'm curious. So you talked about some results that students of yours came up with. What was the sort of format, the setting in which you were working with students on this problem? Is this a class? Is it a research experience? When were you working with these students?
Yeah, so I applied for one of the KERM mini grants, which I highly recommend if faculty are interested. And so I applied in 2015, when I was coming to Williams College. And so as part of that program, you get to have a course in which you do research with students. And so I found 7 eager students to work with me on these kinds of projects. And so you saw the results of one group of students. And then you saw Anthony Simpson, who worked on the juggling. He also worked on other problems related to Kostant's partition function. So from that one semester work, I think we ended up having like 5 research publications out of it.
Wow.
And so, yeah.
That was some years ago now, yes? So,
yes. So
have those students graduated and gone on, any of them pursuing mathematics beyond?
So one went to a university in Chicago for a master's degree. We've kind of lost track. The other is teaching. So the 3 that you saw the results from, one went to get a master's and 2 went into education. Anthony now works at Facebook. So I'm always like, now you get to buy the meals, you know?
Right.
Like, you need a secretary, I'm happy to bring you coffee. So yeah, they're doing phenomenally well.
That's great. Well, I do see a couple questions coming up. There's a question from Tyler about how long did it take the 4 of you to establish the bijection?
Oh my goodness. Okay, so the story goes, I had data and evidence since 2013 to support that this conjecture should be true. And my collaborators, Eric Insco, Mohammed Omar, and I had worked on partition function problems before and had seen all of this data. We didn't know how to prove it. And then we went on to prove other people's conjectures and did other, fancy things with Alexander Diaz-Lopez as well. And I kind of put that project on the back burner. And there was a square, so an AIM square. We were supported by some funding from the American Institute for Mathematics. And then I said, there's this problem and my thesis student wants to work on it. We should collaborate on this. And so we started working again on it about 2018. And so it took us about a year for the juggling stuff to kind of materialize. And, the key insight is there. And then all of a sudden, extending it to the other Lie types was a little bit more challenging.
Yeah, that's
but
great.
We did it. But it took about solid 2 years.
That's excellent. Good. And then I see there's a question from Aaron, who seems to know you, right?
Oh, yes. So have we tried limiting the heights of the juggles to see if any other interesting results pop up? So that is a good question. And the answer is I have not done that. But that might be interesting because it means you have to toss a lot shorter. And so what that would do in terms of the vector partition function is it would eliminate some of those columns of the matrix. And so I think you can do it. And it's just a matter of figuring out how the restriction of how far you can toss the ball, like how high you can toss it, how that then deletes a column from your matrix. And so, yeah, we should look at that.
Excellent. Okay, so a new question. Let's see. I'm scanning to see if there's any other questions that have come up. I don't see any other questions, so maybe that's it for our Q&A, but, oh, sorry, there's one more from Kathy about extending to non-crystallographic cases.
That is a good question. My guess is that, yes, we should be able to. It might require us to figure out how the juggling changes. So just to give you some context, when we switch the Lie types, so as soon as you go away from type A, it actually requires you to have 2 conveyor belts. So one conveyor belt that's coming up and one conveyor belt that's coming down. But the objects that are coming up, you don't get to redistribute. And so my guess is yes, but it might require some additional constructions.
Okay, interesting. Okay, anything else that we want to pull out from the Q&A from the chat? I think we've covered most of the questions. Well, thank you so much again, and thank you for all who participated. Again, I think we have, there we go. We have the link to the chat. Okay, so we have some links to copy of Dr. Harris's book, and I think we're also putting a link to the post-event survey, which we would appreciate if you can take a minute to complete, and show up again in a few weeks when we have our second distinguished lecture on February 23rd with Dr. Alexander Diaz-Lopez. Meanwhile, thank you again so much, Dr. Harris. It's been a real pleasure and just a wonderful experience. Good night to everybody.